Hi there, today we'll be looking at mapping and functions 2, and in this video we'll be looking at the following subtopics: general representation of mappings, we'll be looking at special mappings, composite mappings, and inverse functions. So let's take a look at general representation of mappings. Under this we have some subtopics: arrow diagrams, parallel axis, and lastly the Cartesian graph. So let's look at arrow diagrams. A function in terms of x maps out images in y. We can use arrow diagrams to illustrate this relationship and show how each element in the domain connects to elements in the range. Of course, we are familiar with this kind of representation, and it is called an arrow diagram. Moving to the next form of graphical representation, we have the parallel axis, which are actually number lines drawn parallel to each other. One of these number lines are the domain, while the other is the range. After evaluating the function, we then use lines to connect numbers from the domain to numbers in the range. This connection is made possible by obeying the mapping rule. An example of a parallel axis is what you can see on your screen right now. We can see that arrows are progressively drawn from the domain to connect to the range, and this is done by obeying the mapping function. Next, we have the Cartesian graph, which is our third option for graphical representation of a mapping. Plotting the function using the table generated, we arrive at a graphical representation of the function y equal to x squared plus 1, which is indeed quadratic. Let's move on to special mappings, under which we are looking at identity mapping, which takes an element to itself. This means that an identity mapping is a 1-1 mapping as well as an onto mapping, with equal number of elements in the domain and range. Next, we have constant mapping, which outputs the same value irrespective of the elements in the domain. We can observe in our arrow diagram that every element in the domain outputs one element in the range. A raised to power 0 is an example of a constant mapping. Next, we move on to composite mapping. Composite mappings of functions are actually functions which are nested in another function. Y is equal to 2 into x plus 1 is an example of a composite mapping, because for every input of x, we must evaluate x plus 1 before we multiply it with 2. Hence the name composite mapping. Let's look at an example. When we have two functions, f of x equal to x plus 1 and g of y to be equal to y plus 1 all squared, we are required to find g of f of x. This means that we are to evaluate f of x within the function of g before applying g itself. Hence, we substitute x plus 1 for y. Evaluating that, we have x plus 2 all squared. Expanding, we have x squared plus 4x plus 4. Second example. We are required to find g of f of x and f of g of x when f of x is equal to 2x squared minus 3 and g of x is equal to x plus 1. The first sub-question, we are evaluating g of f of x. This leads us to substitute f of x into g of x. During our evaluation, we have the result 2x squared minus 2. Now we would proceed to f of g of x. This time around, we substitute g of x into f of x. We expand the quadratic term before multiplying by 2. Our final evaluation gives us 2x squared plus 4x minus 1, which is actually different from our previous answer. We can observe that g of f of x is not equal to f of g of x. This means that composite functions are not commutative. We can easily test for commutativity when both functions have the same variables, but this might not be possible when both functions have different variables. We need to take note of this fact when handling questions. Next, we look at inverse functions. An inverse function helps you to connect an element in the range back to the domain. We are used to calculating for images from the domain to the range, but with the help of an inverse function, we can actually do the reverse. By implication, the domain of the function is the range of its inverse function. The arrow diagrams help to illustrate how inverse functions work. So let's take an example. If you have a function f of x to be equal to 1 over 2x minus 3, and we are asked to find the inverse function, which is f inverse of x, what are we supposed to do? We would actually replace f of x with another variable, say y, so that we have y to be equal to 1 over 2x minus 3. Our goal now becomes to make x the subject of the formula. So we move minus 3 over to the left hand side and we multiply both sides of the equation by 2. This will give us 2 into y plus 3 to be equal to x, which indeed means that x is equal to 2 into y plus 3. This has become our inverse function. With this function, if we input values from the range, we will actually get values in the domain. Our resulting equation reveals that x is actually a function of y, and f of y is actually the inverse of x. Hence, f inverse of x is actually equal to 2 into y plus 3. And this is the function that maps elements in the range back to the elements in the domain. So that's all about inverse functions. What you are actually doing is to make the independent variable the subject of the formula. Next example, we are looking for the inverse function of f of x, which is equal to x plus 1 all over x minus 2. So our goal is to find f inverse of x. What we simply do is to replace f of x with y. There is a condition imposed for this mapping that x cannot be equal to 2. We don't need to bother much about that because our goal is actually to make the independent variable x the subject of the formula. Of course, we cross multiply, expand, collect like terms in our attempt to make x the subject of the formula. When we factorize x from the left hand side, we have x into y minus 1 to be equal to 1 plus 2y. We then proceed to divide both sides by y minus 1. Hence, x is equal to 1 plus 2y divided by y minus 1. Let's not forget that x is a function of y, and f of y is also f inverse of x. This means that f inverse of x is actually equal to the result we obtained earlier. You can actually lay your hands on any function and try to make the independent variable the subject of the formula, and that gives you the inverse function. Thank you very much for watching, and see you in the next video.